All right, welcome back, everybody. Hope you guys had a good weekend. We're going to get moving again on the lecture 2 on linear regression. So just to review where we were last time, we have a scalar target variable, which is the thing we're trying to predict. We have a vector of features, which are the things we're using for that prediction. And we have a model that says that if you do some linear combination of those features plus add an intercept, that we hypothesize that this is a decent model for the true target. And this is how we're going to approach the prediction in this unit. And this is not an equal sign, this is an approximately equal sign, so we recognize that there's a difference between our prediction and the truth. And we give a name to our prediction. Maybe I can put the little triangle. This is a definition. We're just calling this prediction y hat. And we also can talk about the difference between the truth and the prediction, which we call the residual, and we can name that epsilon. And the next thing we did is we packed things together in vectors and matrices. So here we're looking at the ith example in the training data set. So here we have the ith example of feature 1, ith example of feature D, and we have all the features in between. And this is going to be the ith, or the prediction of the ith target in our training data set. And so what we did is we wrote this as an inner product between this vector here and this vector of coefficients beta. Here what we're doing is we're separating the things that we were given that are known from the things that are unknown that we need to design. And we can continue this by stacking each of these different predictions one on top of another until we have all the different predictions for our training set, because we have n elements in our training set. And if we furthermore stack all these rows, we get this A matrix. This A matrix, we call it the augmented feature matrix because it has the features, but then it also has this extra column of ones. And then this vector here, we're going to call that boldface beta. And from here, we can combine this and see that this is just a nice simple equation that says the y hat vector is the A matrix times the beta vector. And this is what we use for training, because for training the y hat and the A are known. We're trying to figure out what is a good beta. But then maybe after we're done training and we've selected our beta coefficients, what we can do is if somebody gives us a new feature vector x, we can predict the target corresponding to that x. Okay, so this is what we use for training, and then this is what we would do after training is done.
And that formula for y hat applies to different types of machine learning, like if you want to do reinforcement and
No, we're just starting with linear regression. We don't do anything with reinforcement learning in this class. So yeah, we just want to kind of start with where we're at and try to understand the simplest possible case well for right now. Yep. Okay, so that's what we did last time, and then we said we need a way of choosing these parameters beta, and we are going to use the least squares fit to the data. We're doing this because it is one of the simplest approaches. We can do derivations analytically. We don't need to run complicated machine learning algorithms to figure out the solution. And so this is sort of what it means to do a least squares fit. We want that the sum over the training data of the differences between the true and predicted targets squared is minimized. And we also know that this y minus y hat can also be written as eta, so this is just another way of writing it. And if we want to visualize this, this would be the visualization for the case when D is 2, when we have two features. And so we have maybe feature x1 on that axis, x2 on that axis. And then we would have three coefficients, beta 0, beta 1, beta 2. And beta 0 would change the intercept, so where this plane crosses the y-axis. And beta 1 would change the slope in this direction, the slope of the plane in that direction, and then beta 2 would change the slope of the plane in that direction. And as you change those beta 0, beta 1, beta 2s, what happens is this plane tilts in different ways, it shifts up and down. And our objective visually is that when you look at, okay, the black dots are the true targets yi, and the prediction y hat is on the plane. So we want to minimize the sum of the squared distances from the dots to the plane. So some of them are below, some of them are above. And we want to tilt that plane and shift that plane up and down until this sum of squared errors or squared residuals is minimized. So that's the main idea. If you can understand that idea, that's really what we want at this point. What questions do you have on this? Is it making sense? Okay. If it's making sense, that's great. Then what we need to do next is figure out the math behind it. How do we actually do this? But I think it's really important to understand what we're trying to do before we even dive into those details. Okay. So sometimes we'll call this the regression plane. That's that gray plane, and we have the intercept and slope coefficients. Okay. So this is the RSS, residual sum of squares, that we're trying to minimize. We can also express this as a norm. If you remember what we did in the last unit, we said that the Euclidean norm is going to be the square root of the sum of the squares of a vector. And so here I'm just using x as an example, but this holds, for beta or y or anything. And we can visualize this as follows. Maybe this is the origin here, and this is the vector. And so the straight line distance from the origin to the end of that vector squared would be equal to each of these coordinate dimensions squared. Okay, that's essentially what this says. And if you look at this and apply this definition, how can we write the RSS as a norm? So here's RSS. Here's the definition of a norm. Maybe I'll give you a hint that if that's the definition of a norm, then the norm squared would simply be this. So how can I, using the norm or norm squared, how can I write this over here in terms of a vector? So let me ask this to, is Josh Wolf here? Yeah, what do you think?
Best guess, I was writing this down, would simply be y minus y, like the norm of y minus y hat.
Exactly. It's a squared norm. It's a squared norm because without the square, we need a square root, but if I square both sides of this, then the square root goes away. Okay, so this is another way to write the RSS. It's maybe a little bit more elegant than with the sum, and sometimes we use it for different reasons. It gives us some intuition. Okay, so let's step back for a moment and reflect on what we've done. And this is actually just an example of a generic recipe that we're going to apply over and over again in this class. And this is sort of what you do for supervised machine learning. You assume a model with some parameters. In our case right now, it's this linear model. You get some training data. In our case, we have these XY pairs, n of them. You choose a loss function. In our case, we've chosen this RSS loss. And finally, you find parameters that minimize the loss. So in this case, find the beta that minimize RSS. So right now, we are at this last step. We need to figure out how to do this next. All right, so let's pause for a moment and think about the simplest case, which is what happens in one dimension. So let's just imagine that all I'm going to do for right now is optimize the beta 0 parameter. And if you imagine that RSS as beta 0 alone, as that function, looks like this parabola. So from this picture, you can see that the minimizing value of beta naught would be down here. Maybe I'll call that beta naught hat. And something special happens at the value of that minimum. Besides the function going to its lowest value, can you guys see something else that's special that happens at that point?
RSS is 0.
RSS is not 0, so 0 is down here. So the RSS is not 0.
The derivative of 0.
The derivative, yes, exactly. The slope of this curve at that point is 0. So that is the strategy we're going to use over and over again in this class. Anytime we have a differentiable function like this, we can find the location of the minimum by finding where that function has a derivative that goes to 0. So that would be the simplest case in one dimension. If we make it slightly harder and do it in 2 dimensions, maybe I have beta 0 here and beta 1 here. The exact location of the minimum is a bit hidden, but you can see it's where these cost contours, it's the center of those ellipses. It's somewhere down over there. And right at that point, the slope along this coordinate axis goes to 0, and the slope along this coordinate axis also goes to 0. So essentially what you're seeing is that this is happening in both the variable beta 1 and beta 0 simultaneously. So if we extend that idea, what we can do is we can make a vector of partial derivatives. If we have d plus 1 coefficients we're optimizing, we make a d plus 1 length vector, where each term in that vector is the partial derivative with respect to one of the adjustable coefficients. And we want that this entire vector goes to 0. This vector is known as the gradient vector, and we denote it with an upside-down triangle, which is also called a nabla. But this gradient of RSS with respect to beta is just the vector of partial derivatives with respect to all the elements in beta. Yes?
So this gradient vector is a vector of the beta values that are closest to the true values?
No. This is the slope.
Okay.
So the first element is the slope in the beta 0 direction.
Okay.
The next element is the slope in the beta 1 direction, and so on.
But those values help get closest to the true value?
So it's like, imagine that I look at the slope right here. It would be positive, right? If I look at the slope right here, it would be negative. If I look at the slope right here, it's very special. It's the only place where the slope is 0. And that is what we're looking for. So for this, what we want to do is we want to find the value of the beta vector that makes this entire gradient vector 0.
And once it's 0, what does that represent?
That means that we are at the bottom of our cost function, our RSS.
Okay.
We have found the betas that are at the RSS minimizing point, which is what we're trying to do.
Okay.
Yeah, that they have the smallest average squared prediction error.
Okay, and that prediction is closest to the true value?
Yeah, the prediction error measures relative to the truth.
Okay.
So yeah, that's right. The prediction is closest to the truth in the sense of average squared
Yes.
differences. Exactly. So there's some other technical reasons why this works. If you're familiar with this stuff, in order to really claim that this is the right thing to do, we need to know that this is a convex function that's differentiable and blah, blah, blah. We're going to talk about those details in Unit 6. For now, we're not going to get bogged down in those details. We'll come back to them later. But there is a little bit more to the story. Another thing about the gradient vector, it's helpful to know, is that it points uphill wherever you are. So, for example, these arrows show the gradient vector, and this is again 2 dimensions, beta 0, beta 1. So when we're, let's say, right over here, the gradient vector is pointing in that direction, which means if you want to, if you're sitting there and you want to go uphill at that point, you want to travel in that direction. If you're sitting here and you want to go uphill, you want to travel in that direction. Gradient always points uphill. Also, the norm of the gradient tells you how big the slope is at that point. So you can see as you go to the edges, the gradients get longer, the norms get larger, which means that it's steeper over there. You can also see that here. As you get to the corners, it gets steeper. When you're close to the center, it's not that steep. And so you can see these gradients are quite short. And when you go to the very minimum, the gradient is exactly 0. Yes?
It's possible to have like multiple bottoms.
Multiple minima?
Yeah.
Yeah, that's a great question. So for RSS, it does not happen, but it can happen with other cost functions, and that's what we're going to talk about later in Unit 6. We're going to get into all those details, exactly, multiple local minima. Okay. All right, great questions. Another one.
Is there any reason that you chose squared error over absolute error?
Yeah, so great question. The reason we're doing squared error is because it's the simplest thing to analyze. So it turns out if we tried to do this with absolute error, the issue that we would one issue is that we could not apply this procedure because it's not differentiable. Because it's like absolute error looks like that, and it's not differentiable down there. We couldn't derive the solution. You'd need to run an optimization algorithm to find the solution. We're going to talk about that in Unit 6, but for now, we're going to try the simple case where we can derive everything. Yeah. Any other questions? Great. Okay. So let's get ready to do this gradient zeroing thing we're talking about. Let's begin by writing our RSS in a way that's going to enable us to do the calculus. So here is the original definition of RSS, the difference between the ith training target and its prediction sum squared. And let's write this in terms of the beta j numbers because as you can see on the left, we have the entire vector of beta. And unless you guys know how to do vector calculus, which is something that probably most of you don't know how to do, we want to write this back in terms of scalar beta so that we could do the familiar calculus. So in order to write this in terms of scalar beta, we have to go back to our equation. If you remember, our equation in terms of the vectors was y hat is matrix A times vector B. And so that means if you look at the ith coordinate, you get y hat I is the sum over j of aij beta j. And that is the equation we need to plug in here. I'll be more specific, so j is going from 0 to d, and we have aij beta j. Is everybody okay with this thing in the top right? Okay, so this is the equation. And now you can see we've written the RSS in terms of the individual betas. That means that we can do these partial derivatives, because the betas have been exposed. And we're using the little aij to mean the ith row and jth column of this matrix A. Okay. All right, so now we have to get into some calculus. And this kind of calculus stuff we're going to be doing over and over again. Question?
Sorry, why do we have the sum start at j equals 0?
Because our first beta coefficient, the intercept term, is beta 0.
But then what would it look like
In the matrix?
is it because
Yeah, let's take a look at the matrix. So this would be the first element of the matrix. It's always a 1. Right? Yeah, this is when j is 0. So j goes 0, 1, dot, 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 to d. Yes. Okay. So here we are. We want to do this partial derivative. So one of the important things to remember about differentiation is that it's a linear operation, which means if you want to differentiate a sum like this, the derivative can be moved through the sum. In other words, the derivative of a sum of terms is the sum of the derivative of the terms. Okay. So when we do this partial differentiation, we just move the derivative through the sum, we write the sum here, and then we work on the derivative of this quadratic term with respect to beta j. Is everybody okay with that idea? Okay. So how do we do the derivative of this with respect to beta j? We need to use the chain rule. So if you remember, the way that the chain rule works is the derivative of this squared term is going to be 2 times the thing in the square times the derivative of the thing in the square, in this case, with respect to beta j. Right? So chain rule is 2 times this times the derivative of this with respect to beta j. So here I have the 2 times this, but I wrote it a little bit more compactly. Remember, this is just y hat I times the derivative of the thing in the square with respect to beta j. Now I did something else here that I want to point out, which is that I changed the sum variable from j to j prime. And let me tell you why I did that. J is a very specific constant that we have chosen in advance in order to even define this derivative. For example, we might think maybe j is 0. So j is just some number we're choosing to do the derivative of. If I also would have written j up here, it means I'm using j to mean 2 very different things simultaneously, and that can lead to a lot of confusion and mistakes. So what we've done is we've said, let's not use j in 2 places, we'll use j here, and we'll use something similar to j but different. I've called it j prime. But you could have used anything else. You could use k, just as long as it's not some other variable like I, which is already in use. Okay? So that's what we've done here. Instead of writing it this way, we've written it with the j prime. And hopefully that makes the next step a little bit simpler. So we need to do this partial derivative. So I have basically a sum of 2 terms, so that's the derivative of the first term. So what is dyi d beta j? Let me ask this to Yatish Shiradana Holly. Yeah. So what is this term? Zero. Exactly. That's easy. Let me ask you then, what is the derivative of the second term? So here, we want to use the idea that, again, this is linear. So I can move that derivative through the sum, and then I'm just looking at the derivative of this with respect to beta j. So now there's 2 cases. Either j prime equals j, or j prime does not equal j, right?
Yes.
If j prime does not equal j, what's the derivative? 0. And if j prime equals j, what's the derivative?
The coefficient of
aij.
that. Yeah.
aij, exactly. So, so let me just summarize everything. So we have the sum. We have 2yi minus y hat I. And then finally we have a negative. Let me put the negative right up front. And finally we have aij. Okay, so this stuff, these derivations are things that can show up on homeworks and exams. So it's something I'm assuming you guys will be able to do this. Yes?
Is the summation supposed to go from I equals 1 to n, not I equals 1 to 1?
So this one goes from I equals 1 to n. Oh, yeah. Exactly. Thank you. Yeah, so pay attention to these derivations and make sure that this is stuff that you can do. And we're going to see lots of examples of this and some other things. Okay, is everybody good with how we went from here to here? Yes.
Can you explain why the partial derivative yi was 0?
Yes. So yi is just a training quantity. It's just a number that I have, gotten from a data set. And that number is completely independent or irrelevant, unrelated to this beta j, this thing I'm trying to design.
Okay.
So when I change beta j, like this doesn't change at all. Yeah. Okay. Any other questions? Okay, great. We'll see this again soon. So we now have an expression it's this derivative, but we want to massage this back into the world of vectors and matrices. And so let me take this step by step. I'll do this down here. So if we have, I'm going to ignore the -2 part. I'll just work with the rest. Oops, sorry. So we have, we have a sum over I, yi minus y hat I times aij. We want to write this in terms of matrices and vectors. That's our goal. So there's a couple different ways to do it. We want that I is the inner index. It is the inner index right now. We can also do this a slightly different way. We can exchange the order. We can bring aij here. And put our y's there. But if you do that, you can see that the inner index of this one is no longer I. However, we can fix that. Let me just erase that term here and write it as the matrix A transpose jth row ith column. Okay, so this guy, remember, this is just aij. And so now we have the inner index here and here. And let's again write this in terms of vectors and matrices by making some pictures. So here's the A transpose matrix. We have J coming down the rows, I going across the columns, and then we have a vector here. This vector is y minus y hat, and I is coming down the rows. I don't know if, oops. Okay. And so, so finally, what we have is we have the quantity A transpose Y, and we are looking at the jth row and ith column. Maybe to be correct, there should be over here a j and an I. Okay, this is similar to the stuff, the matrix vector gymnastics that we did at the end of the Unit 1 slides. Okay, so let me just review. So we started with this expression over here. Actually, we were just removed the -2 for now to make it simpler. And then we moved the aij to the front, and we wrote it as matrix A transpose ji. And then we said, oh, this looks like a matrix vector multiply. So let's put the matrix here. This is the ith row of y minus y hat as a vector. And this is a scalar. So to this matrix vector multiply, we're taking the jth row and the ith column. And then we're just rewriting it compactly here. A transpose y, jth row, ith column. Oop, actually, I made a mistake. On the right, it should be, I left out the minus y hat. Sorry about that. Oh, yes. You're exactly right. I don't need to worry about I at all. I just need to worry about J. Sorry about that. So that's true. This is a summation over I. Oops. Summation over I. So there's no more i's, but there is a j. This is a vector, and we are just looking at the jth element. Okay, so this is what we have. And then we're just, that's what we've derived here, and we're adding back a -2 that we left off before. And then there's a last step, just to bring it back in terms of the betas. We're going to replace y hat with a times beta. Okay, so to summarize, we have that the jth partial derivative of the RSS is a particular vector where we look at the jth element. Okay, everybody good so far? All right. The reason we're doing it this way is that, remember, our real goal is to set all the partial derivatives to 0. And so we found that if I look at the jth partial derivative, that means it's this vector, jth term equals 0. So if I want this to happen for all terms, it basically means that that entire vector must be 0. So that's what I have down here. A transpose times the quantity y minus a beta. Here I'm being specific and saying this is the least squares solution.
Is that beta IS?
LS.
LS? Oh, LS.
Yeah. Okay, so this is what we were able to derive. And so now we're almost done. We can expand this further as A transpose Y minus A transpose A times beta LS. And if I have 0 equals this, then I can bring this negative term to the left side, and I get this equation. And one more step. Let me see, is Yafet Atzbaha here? Yafet? No. What about Bruce Cheng? Yeah. So how can we write beta LS from there?
A transpose A inverse.
So, okay, there's no such thing as this because A transpose is not necessarily a square matrix. So there is no such thing as A transpose inverse. So what else could we do?
A transpose A's inverse.
Yes, exactly. We can invert A transpose A and multiply it by both sides of our equation. And finally, we get an expression for our least squares coefficient vector. And this is something that might be difficult to do by hand, especially if we have lots of training samples and lots of coefficients. But it's something that's pretty straightforwardly done in MATLAB or Python via NumPy. It's a pretty routine calculation. But we were able to derive this expression by hand in this RSS case. Yes?
Why there's no A transpose inverse?
A transpose is not a square matrix in general. So, yeah, when you can only invert a square matrix. Yeah. Okay. All right. Is this making sense? We've gotten into some of the more difficult stuff. Here we're doing calculus, linear algebra. This is sort of the flavor of a lot of things we'll do in this course. I know at the beginning for a lot of students, there's a lot to take in, but it's the sort of thing where if you practice on the homework and see more and more of these in the lecture, I believe it should start to click. But it is really important to understand every step along the way. So if you do have questions, please do reach out via office hours, mine or the TA's, discussion boards. This stuff really is important to understand every step along the way.
Did you say you'd be giving memos for the homework?
Memos, what do you mean?
For the homework, like solutions?
Oh, yeah, the solutions are going to be posted too, yeah. Mhm. All right. Okay, everybody's good? Any questions on anything we've derived? Okay, great. So, so we have this equation that we derived, which is nice. It's something we can program, but it's not very insightful. When you look at this, to me it looks quite confusing because this A matrix, it has some features, but then it has this column of ones. It's really kind of difficult to see much meaning in this expression. So we want to instead view this more from the perspective of statistics, and so that's what we're going to do next. And in order to make that possible, we're going to have to change our notation just a tiny bit to account for the fact that the slope coefficient operates in a very different way than the rest of the coefficient, or the intercept operates in a different way than the rest of the coefficients, the slope coefficients. In other words, we have beta 0 plus, we're going to make a new vector. We're going to call it beta sub 1 through d, transpose x, and this beta 1 through d is going to contain beta 1 through beta d, but it is not going to contain beta 0. Okay, so you can see that this one is just sort of a shift, and then these guys are slope coefficients that are multiplying against the feature values in the x vector. So that's why they have very different functions, and we're kind of notating them in different ways. Okay, everybody good? All right, so let's dive into some of the statistics that we're going to need. So this too is something that I assume you guys have seen sometime before. Let's start with the simplest statistic, the sample mean. So if I have a vector of numbers y1 through yn, and I say what's the mean of my training targets, all we do is we add up all those values, there's n of them, and we divide by n. So we're going to give this the name y bar. That's going to be the sample mean. That's going to be our notation for the sample mean. We can do something similar for the sample variance of the j'th coefficient. Let me ask this to, is Lucas Caret Delgado Pinheiro here? What about Mihai Krisan? All right. This is a little more difficult. So, yeah, how do I write this? This is the sample mean of the j'th feature.
Would it be sum over, I equals 1 to d?
So we're going to sum over our data. I is a data, n examples of our data. We're going to still sum that way. But what are we going to put over here?
X sub I.
But we actually have different features. We have different examples I and different features j. Right? So there's actually xij. That's the ith example of the j'th feature. And then finally we're going to average by 1 over 1. Okay. Yeah, so that's the sample mean of our targets from the training set, and this is the sample mean of the j'th feature from the training set. Everybody good with that? Okay. Let's go to the slightly more complicated statistic, the sample variance. So for the sample variance, what we're going to do is we're going to do another average over our training data, but the thing we're going to average is going to be yi minus its sample mean. Okay, so this thing here is what we're using for that y bar. So here we're looking at the average squared deviation between y and its mean. And we can do the same thing for the jth feature. That would be the average over our training set of xij minus its mean x bar j. Okay, and a little bit of, are there any questions on variance? Okay, so here's just a little picture that shows examples of histograms of two variables that have, perhaps they have the same sample mean, but this red one has a small variance and the blue one has a large variance. So its average deviation from the mean is larger in the blue case. Okay, now some of you guys might notice that we're using a 1 over n here, whereas it is possible in some cases to use a 1 over n minus 1 when defining the sample variance. We're going to talk in more detail about that in Unit 3, but for this unit, we definitely need to use 1 over n. We don't want to use 1 over n minus 1 because if we did, then all the equations would be wrong. So there's definitely a time to use this, and we'll talk about 1 over n minus 1. We'll talk about that later. Okay, another thing about the sample variance quantities is that they're squared quantities, and so that makes them a little bit less useful for interpretation because sometimes, you know, if you have, let's say, you know, weight or something in pounds, then this would be like squared pounds. So and that's maybe you just want to work with pounds. So what you do is you just divide the variance, or you take the square root of the variance, and that's where you get the sample deviation. The sample standard deviation. So sometimes we'll use variance with the squares, and sometimes we'll use standard deviations, depending on which one is more appropriate for us at the moment. Okay, any questions so far? Okay, so we have the mean looks at y alone, the variance looks at y alone, or x alone, x alone. We also need to know the relationship between the x's and the y's, and for this we can use something called the covariance. This has a form that is similar to the variance, similar to the variance, but you take xij minus its mean times yi minus its mean. Okay, so this is one way of measuring the relationship between those two quantities. All right, so we got the mean, variance, covariance. Another thing I want to emphasize is that these are not, we're not dealing with any random variables. So some of you are familiar with random variables and what we would call the statistical mean, the expectation. We're not doing that here. There's no random variables here. All there are lists of numbers. You're just taking the arithmetic average, that's all. We will deal with expectation and so on later, but for now, we're not doing that yet. Okay. Any questions on these quantities? Okay, great. So now, as you know, we're really dealing with vectors. So here we have the vector, entire vector of different feature values for the ith example. So we can actually look at the average across our data set of those vectors, and that gives us this boldface x bar. When you look inside that vector, you will find the scalar sample mean of the individual features.
So when we're writing this on head, for the sample mean vector, would you want us to have a bar at the top and a bar at the bottom?
Exactly. Bar at the top and the bar at the bottom. Yeah, so for those of you guys who write vectors like this, I don't recommend that in this class because that clashes with the sample mean. So I recommend not doing that. Instead, doing underline. Okay, so that's a sample mean vector. We can do something similar with the variance, looking at the variance of a vector, roughly speaking. So you take xi minus its mean, xi minus its mean again, but here, in order to make a valid matrix multiply, we have to transpose it. So let's just think about this. We have a column vector times a row vector. When we do that outer product, we get an entire matrix. So this thing is an entire matrix full of different quantities. When you look along the diagonals of this matrix, the jth diagonal term is the variance of the jth feature. So along the diagonals, you have variances. When you look off the diagonals, you have covariances between different features. Like the jth row and kth column is the covariance between the jth feature and the kth feature in your data set. Okay, so we got our sample mean vector, sample autocovariance matrix. And finally, we can do our sample cross covariance vector, which is an extension of this idea to vectors. So we basically just change this part here to a vector. So here we have our vector x. Our y's now, we just have a scalar target, just one target. So when we do this, we have a vector times a scalar. That gives us a vector. So this thing is a vector. When we look at it, let's look inside it. We have Sx1y, that's the covariance between x1 and y. The first feature in y, Sx2y, and so on, all the way to Sxdy. Okay, so those are all the statistical quantities we need. We don't need any more than that. With these, we can fully characterize what's happening in linear regression. Yes?
Why wouldn't we want to capitalize the cross covariance vector?
It is a boldface S. Oh, why don't we capitalize it?
Right.
Because it's a vector, not a matrix. So usually I reserve the capital for matrices.
Thank you.
Okay. Any other questions? Yes.
So we are doing the autocovariance to find out the relationship between the features.
Yeah, this one contains the relationship between all the features, and this one contains the relationship between the features and the target. Both of them are important for what we're doing. Great. Any other questions? Okay. So let me show you some other expressions that are useful because they come up in derivations quite often. So this is the derivation we started with for the covariance. If we expand that, we can expand this thing. We have xi times xi transpose, that's the first term, minus x bar times xi transpose. That is the second term. And notice that in writing that second term, I moved this, which is I dependent, through this x, because this x bar is not dependent on I, so I can just move that through. And that helped me interpret what this is. Does anybody see what is this quantity here? That's right, it's the mean vector. X vector bar. And of the quadratic, we still have two more terms. There's xi times x bar t. So here's our xi x bar t. This summation, is a summation over I, so it affects this. We can think of this as separate from that summation. We can do the summation here. And once again, recognize that as our mean vector. And the last term in our quadratic is x bar transpose over here. And now we can actually notice that there's some cancellations. This term is the same as this term, which is negative of this term. So basically, this cancels this, and we're left with that. And we can write that as, make sure. Okay, so we have 1 over n. X equals 1 to n. xi transpose minus x bar transpose.
So how do those cancel out exactly? Is one side?
We have minus x bar transpose,
Yeah.
right? Plus x bar transpose.
Oh.
Yeah. Yeah, so basically you can either write the covariance matrix by subtracting the means, before you do the multiplication and the sum, or you could do this summation without the subtraction, but then subtract it later. So both of them are equivalent. So sometimes in derivations you come across this, and you want to write this in terms of statistics. Well, that thing equals capital SXX plus the outer product of the means. So that is often a shortcut to getting from here to statistics. Okay, any questions? Everybody go to that? All right, finally, we'll do something very similar with the cross covariance. So this is the definition we started with. We can expand this into xi, yi here, x bar yi here, and then xi y bar over here, and then x bar y bar over here. And in these middle terms, we moved the sums through the x bar, which didn't depend on I. And so what do we call this guy? The average of the yi's is? What's the average of the yi's called?
The sample mean of y.
Yeah. How do we write it? Y bar, exactly. Y bar, and then over here, just like above, we have x bar. And once again, let's see. This one cancels this one. And so we just have the first term and that. Okay, is everybody good with this? Okay. So the next thing to do is to do our partial derivatives again. We can I think we have time for the first one. So we want to take the partial derivative of our RSS with respect to beta naught. And if we set that to 0, that should give us an equation of optimality. So here's our RSS, and now I've written it in a different way. This is the new way that I write y hat, or minus y hat. I. So we're writing it in terms of the beta naught and the slope coefficient stuff. So how do we do this? Let me ask this to, let's see, is Ethan Lawrence here? Yeah, all right. So what's the first step? Can we move this forward? Move it, yep, through the sum. And then I want to take the partial derivative of this with respect to beta naught. How do I do that?
First term should be 0.
So it's chain rule because of the square.
That's only 2 times whole interior.
So we keep the sum. Yep, and then we got 2 times the whole interior, yi minus, and I think here I'm going to do, I'll write everything out. Beta naught minus xi transpose beta 1 through d. And then finally, I have partial derivative of the inside, which is, with respect to beta naught.
The first term is 0.
Yep,
Should be
minus 1. That's it, because the last term is also, there's no beta naught in that. So all we have is a minus. We can put it out front. Okay, so that's one of the equations we'll need, and next time we'll work on the others and put everything together. All right, have a good night, guys, and we'll see you on Wednesday. X1 through XD.
Not I or J or something.
I is like a temporary variable that we use to count the number of examples, but it's a temporary variable. And J is a temporary variable that we often use to count the number of features. But the total number of features is D. And the total number of samples is N.
Okay, I see. So that's a simplified word about the dimension, right?
Yes, exactly. D is the dimension of our coefficient vector.
Okay, got it.
Yes. And then N is the dimension of the samples.
My iPad don't have a chart. Can I take a picture about this slide 19? Thank you.
Quick question. So when studying like the derivations, you don't want us to memorize them, you just want us to understand every step, right? Like when we study.
Yes, if you understand them, you wouldn't need to memorize them.
Obviously, that's
because my tests usually have a variation on this. It's not exactly the same, but it's like, you know, in spirit it's the same, but the details differ. So if you just memorize the derivation and repeat that, it won't match the test. But if you know how to do it, then you'll have no problem.
That makes sense. All right, that's what I wanted to know.
So I was just wanting to schedule through SLPS today. I was going to schedule it for Monday, but then I remember when that was the natty was that day. So I scheduled it for Friday at 2:30 before.
That's fine.
I just wanted to make sure.
That's fine.
Like
Yeah.
that lecture, we don't need.
Yeah, you won't need that lecture.
Okay. And then is it just going to be similar to the homework?
Yes, it'll be very similar to homework.
Okay, I'm almost done with the homework. Are you going to have any other practice
The
questions?
quiz is a good practice.
Okay.
Yeah.
All right, sweet.
Yeah.
Hey, thank you.
Sure.
I just had a question on this stuff. How do we go from transpose?
So these are scalars, so I swap them because scalar multiplication commutes, right? So there's a scalar here. And then if you remember, Aij is the ith and jth column of A. So if I transpose A, then I swap J.
Okay.
So that's what I do.
Okay, gotcha. Thank you. Sure.
I just wanted to ask about the homework.
Yes.
So I compared this one with the Fred question 2A, but
Okay.
what about these three among the leaders? Just these ones. I'm not too sure if I'm on the right track.
Yeah, I guess I would need to kind of look closely at what you did and what the question was asking. The solutions are posted if you want to check them out.
Right now?
Let's see. I'm trying to, maybe they're not maybe they come live on,
I thought they would come at like 4:10, like, because that's like when it's due, so like the
yes,
solutions would be
exactly,
posted. Like,
right. So the solutions will be posted Wednesday.
Yeah.
Okay. Yeah.
Okay.
But yeah, I can help you right now if you want. Just let me, maybe he has a quick question.
Yeah, so I was wondering, like, is this material covered for the midterm, or is it just stop at, okay. I got it.
Midterm is unit 1.
Just unit one, okay.
Yes.
So I assume like the first lecture slide that we like went through is all.
Yeah, like we covered it in the very first lecture and a tiny bit of the second lecture.
The tiny bit of this one, okay.
Tiny bit of like
Oh,
last Friday.
last
So
Friday.
unit 1,
Okay.
basically like that lecture packet.
Gotcha.
And now we're on unit 2.
I'm not sure if I'm, like, I was registered with like SLDS before,
Okay.
but I'm not sure if I like need to do something again for like the double time, or whatnot.
I don't know either. I mean, a number of students, I've gotten like accommodation requests from a number of students. I don't remember them by heart.
Yeah.
There's like maybe 5 of them. I don't know if you're in that list or not.
Okay.
If you're not, you want to get in there.
Just talk to LSLDS and then just like
Yeah.
have them send like a whatever, a reminder
Yeah.
email or something like that.
Yeah.
Okay. I would just like, is it like a separate place from here, or is it just like you stay here longer than like time is up?
Separate place because there's
Separate
another class
place.
that comes
Okay.
in.
All right, yeah, thank you so much.
Sure.
Yeah.
I have a quick question about the submission for homework 1.
So yeah, there's no submission because, as I mentioned the first day, like I don't have a grader this term. So the homework is not optional in the sense that it really will help you for the exams and for learning, but you don't need to submit it.
Okay.
Yeah.
Okay, thank
So
you.
it's kind of honor system.
Yeah, because I was sick last week, so I
Oh,
didn't hear
okay.
that. So
Yeah.
I was confused when I was
Um,
looking for the submission for it.
Okay, if you want to hear the first lecture, I recorded it, just send me an email.
Okay.
Sure. You have a question? Yes.
Will the PowerPoint, like the notes you took on, where you put it
Will I post them?
online?
Yes, I will.
Oh, okay, because there's some of them I didn't really put it down.
Okay, yeah, I will. So whenever I finish every one of these units, I post the completed notes.
Oh, okay.
Yes, but I can help you if you have a question.
And so this one,
Mhm.
is this one the column matrix or the row vector?
So whenever we have a lowercase bold variable, it's a column vector. If we want to make it a row, we have to transpose it. So for example, like this is a row because it's transposed column.
Oh, okay.
But this is a column. Yeah.
And this one is does it look like this? This column?
So yeah,
Is the
xi goes from 1 to d
to
because
D?
there's yeah. So yes. So when you let me show you.
I thought column is n samples. There's n samples in a column, right?
Yeah. So if I look at the ith target, that is this inner product between the features for example I and the coefficients. And so you can see this is what you're thinking of. It starts out as a row vector, right? Maybe like you can think about it as a row of this matrix.
Okay.
But here I'm taking that row and I'm making it a column with that because here there's a transpose, there's no transpose.
Oh.
Right.
Oh yes, yeah, that makes sense.
Yeah.
Because I was confusing why it's like D,
YD, yeah.
and then I thought it's like there's n in a column.
So you know, there's different columns, right? Like these guys are columns of this A matrix, so there would be n coefficients here.
Yeah.
But I could take a row like this, and I could transpose it, and that's another way to get a column.
Oh,
Right.
so I have to depend on the context to
Exactly.
see which.
What is the meaning
What
of
does
it?
it mean? Oh,
Yes.
okay.
Yes.
Wow.
Yeah.
Okay, I got it. Thank you.
Sure. Got a quick question?
I was asked about that averaging thing. I'm a little bit confused on why we would average oh wait, we'd be averaging these elements, right?
No, we're averaging this way.
Or sorry, yes,
Yeah.
Why am I saying this? Yes,
Yes.
this way. But why are we averaging this? Because aren't these different samples? Like this is one sample, this is a sample. This is a
Exactly,
sample.
exactly. We're averaging across samples. So like this mean vector is like,
Okay, so we're averaging like that one parameter.
yes. So it might be like, remember our automobile data set, we have like maybe horsepower in one column. So this like X bar J might be like, what's the average horsepower of all the cars?
Okay.
So yeah, it's definitely a useful quantity.
Because it doesn't make sense to average things that aren't the same units also.
That's right, exactly. It doesn't make sense to average it.
And then my next question is with the indexing. So you're saying like in some cases, I think here we started with J sum from J equals 0 to D.
Mm-hmm.
But why are we using D since all matrices started with index 1, 1? Why are we
Not
starting at 0?
necessarily.
Yeah. Why are we starting at 0? I guess?
Why are we starting at 0? We're starting at 0 just because the notation we've established says the first coefficient the intercept coefficient we're calling beta 0. And in order to make it, you know, the A play nice with that, we're saying here that like when you count J, we're always going to start at 0.
I guess like would we be penalized on an exam, say, if I wrote starting from 1, because technically if you write beta sub 1, that means like the first element of the vector beta.
Yeah,
Not
we'll just have to
beta
be,
0.
you have to be a little careful. So, you know, like when you work in Python, actually, everything starts
Yeah,
at 0.
everything starts at 0.
When you work in MATLAB, everything starts at 1. So it kind of depends. We have to allow some flexibility. So what's maybe even weirder here is that if, when we go this way, we're starting at 1, and when we go this way, we're starting at 0.
Okay.
Right? Just because that keeps us consistent with the use. It's a good point you raise. It's
So
good to
just
see that.
notation. But
Yeah, it's notation. We're trying to make it as elegant and simple as possible.
Okay.
Because otherwise it's kind of a mess. If I put this here, yeah, I think this is how everyone else does it too.
Okay.
So be kind of consistent.
But would it matter if I started by 1, or would that be a big deal?
In some cases it kind of would be.
Because we're kind of assuming that J is like somewhere.
Yeah, and we're gonna use this like all term.
Okay.
So yeah, once you get used to it,
Okay.
this will be what makes sense.
That's fine.
Yeah.
All right. Thank you.
Sure. Okay, all right. So let's come back to, yeah, so which problem you were curious about? Problem?
It's question 2.
2, okay.
B. Let's do 2B.
Okay.
So yeah, it's just a lot of information right now, but I'm sure as time goes on, it'll be
Yeah.
easier to.
Yes, it's a lot. So let me just get to like a blank. Okay.
Should I get the question up?
Sure, yeah.
So 2B.
2B. So we have C is B times A, and B is we're given the columns B1 through BD, and A, we're given these rows A1 through AD. Do I have everything? Yes. Okay, so we want a single summation of terms involving those guys. So what I would recommend is draw some pictures. I think visualization usually helps. So let's write the B as we have here.
Yeah.
So we have these like B1 through BD, and these are column vectors, right? And then A on the right, we have A1 through, A, D. And so what's kind of a cool property with matrix or matrix vector multiplication is that we always have, let me just write as an example, like A, B, C, D, E, F. You know that this is A times D
Yep.
plus BE plus CF, right?
Yep.
The same exact thing works here. So in this case, A would be this entire column, D would be this entire row.
Okay.
So what this means is we have a sum, and we can now name any dummy variable we want to do the summation where we go from 1 through D. So I can use J or I or whatever. I'll use J. That's going to index this way.
Yep.
Again, maybe it helps to draw a little picture. And I'm going to have first times first plus second times second and so on, and that's going to give me BJ times AJ transpose.
Okay.
Is that something close to what you got?
I hope so.
You got it.
So then that makes sense, but then when it comes to, I think it's the next question where it's about summing I and J.
Okay, let's check it out.
Is it this C, suppose, right?
Okay.
For C, I, J. Yeah, for the J column, actually this question. The summation of scalar entries B and J. There's one way you're supposed to, okay, I think it is this, because we have D and then we have K, right? So that's different to the example that, no, it's not actually, because that goes D across and then D down.
Yeah, right. Yeah, you got it.
So it's all the same.
It's all different ways of looking at, describing the same thing with different, like, do I want to look at rows? Do I want to look at columns? Do I look at scalar entries? Do I look at the matrix as a whole? Yeah.
Okay.
Mm-hmm.
Before I go, so then with this, because we have N across and then D going down, right? No, D going down, K.
Yeah, let's look at it. So we got this next problem. So this is part B.
C.
Sorry, part C. Yeah. So we have C is B, A again. And we have, so in this case, B1 through Bn. And then over on the right, we have A1 through AK. And the dimensions they do work out in the sense that these guys have D entries from left to right.
Yeah.
And then A has D entries from top to bottom. So we can do the matrix multiply, like this dimension matches this one.
And it's the exact same thing that we did
So,
up here.
okay, but yes and no. So if I have a situation like, let me say A, B, C, D, how would you do this? This is a column, this is a row.
Okay, so it's valid.
First, is it a matrix, a vector, a scalar? What is it?
That's a scalar.
No.
It's not a scalar?
No. So the dimensions are going to be whatever this dimension is on the left and whatever this is on the right. So it's going to be a 2 by 2 matrix.
Oh, so then it makes another 2 by 2.
Yes, it's a 2 by 2 matrix. So what's in the top left?
Top left would be AC.
Exactly. And top right?
AD.
AD. Right.
And then
Bottom
BC and BD.
Exactly. So this is the idea, we'll call an outer product. This is what we're using here.
Okay.
Now, like, this is our A. Okay, our A is like this. Our B is like this. Our C is like this. Our D is like this.
Okay.
So what we're going to get is we're going to get a matrix where the top left is going to be B1 transpose A1. That's like this term. That's just a scalar.
Okay.
And then we're going to do a bunch of other things, and then the top right will be B1 transpose AK. So basically for that, I'm like looking at this times this, then I'm looking at this times the next one and all the way to this times the end. That's what I'm going to see across the top row.
So the answer would have BN transpose times AK.
Well, I mean, the bottom row?
In the corner. That's
The bottom right corner?
Yeah.
That bottom right element, you're right. It's going to be BN transpose AK. What about the bottom left?
The bottom left would be BN transpose and A1.
Right. A1, exactly. So this is an entire matrix, And then these are its different scalar entries.
And that's the answer.
Yeah, yeah.
Jeez. Okay, so I don't know what I'm doing. So
Yeah, I mean, this, don't feel bad, but it is important. It is something to, this is the time to kind of practice it.
okay. Yeah. Can I take a picture of this?
Sure, yeah.
So how would I know when I'm supposed to do what? That's my biggest thing right now, because sometimes I know how to, like how you just pointed it out to the multiplication part of it.
Yeah.
But to identify this versus that, now I'm kind of clueless with that.
So, in the simplest level,
That's a scalar, right?
what are you
This
pointing
this
at?
answer, the solution there.
Um,
No, it's two
no,
vectors.
no, yeah, so this is a column, and then this is a row.
Okay.
So that's gonna give a whole matrix. And that makes sense because this is just a way of writing this, which you can see suggests it's a whole matrix. It's big capitals.
Let me just get my bearings for 1 second. So we just did C, right? And it says an expression for the ith row column. Okay.
Oh, well, we didn't quite do it.
Oh, okay.
So we have the whole C matrix. Now, if we want to know the ith row and jth column, what would it be?
You take the sum of that, right?
Well, so this is a matrix. Now we just got to extract the ith row and bth column. It's just going to be extracting one scalar entry, one of the entries in this big matrix. We're just pulling that out.
Oh, so would you say BIN transpose? Is that
BI, that is the ith row, and then for the jth column, do you see?
say AJ?
Exactly.
Oh, and then it's a wrap.
Yes. So this, another way we could write this is like the C matrix. I'm extracting the ith row, jth column, and it's that scalar entry.
Okay. Okay, I see the difference in the questions now. All right. Let me go do myself some studying.
Okay. Yeah.
Yeah, it's not too intuitive.
Yeah, it's one of these weird things where it just takes practice. Like once you do enough practice, it is intuitive, but before you get there,